without further ado, let's start. So how do modern pinball control systems work? So we will talk about the systems after 2000 somewhere, right? So everything after WPC, I would say. Because WPC has been on old Motorola CPUs, which fine for the purpose they had, but today we expect more from our games, and for that reason that's our agenda today. So what are pinball control systems? It's like an arbitrary term, so let's define this a little bit. Then what are the challenges? So what should they do, and why isn't it trivial? Because in the beginning it might sound trivial. Then we will talk about how pinball control systems look. So I will give you like an overview how they work, and then we will talk about two specific things, and that's commands. So which kind of commands typically exist, and then we will talk about hardware rules, and that's how we counter some of the challenges, which we will talk about in a minute. So to make this a little bit more interesting and interactive, and there are two questions which you might know the answer or you might not, but then you hopefully, if not, you will hopefully learn the answer in this talk. Hi Freezy, how are you doing? So why do my flippers not work with keyboard bindings in MPF? So maybe you have noticed that if you define your flippers in MPF and you enable them, and you run a real game with real hardware, and you got keyboard bindings on your PC keyboard to the flipper button switch, right? And you press your button, nothing will happen. So you press the real button, the flipper works, but it doesn't work if you press the software flipper button. And it's not an MPF bug. There's a reason for that, and we will come to that later. And then the second one, it's more like something to think about. So how long does it take for the flipper coil to become active after you press the flipper button? So you press the button on your machine. How long does it actually take until the flipper then goes up? Just, what do you think? 1 milliseconds, 10, 100, 1000, 0, 1 nanosecond? I don't know, right? Just think about it and think about if it's important, how long that is. And we will also come to that in a minute. So now that you got something to think about, let's start with what are pinball control systems. So pinball control systems, they control your pinball. So we're talking not about the electrical stuff here. We are talking about the software stuff, which then gives a digital output to drive your coil, right? So first, the goal of the control system is to run the game somehow. Even though most commercial systems you buy, they interface to a computer and the game runs there, but still the computer is then part of the control system. Then you need to read switches, so the switch state. So you need to know if a certain switch is active or inactive, or if it changed. And often it's really too important to know from a software perspective if switches changed. So it doesn't matter. I mean, the software doesn't want to ask the hardware every 1 millisecond for all switch states. It just wants to know which changed. That's what software usually wants to know. Then to drive coils, so basically, pulls the coil in your trough to eject the ball, pulls the auto launcher to shoot the ball, and so on. And also actuate the flippers, actuate your pops, your slings, and everything else in your machine, right? And the same for lights. It should be able to drive your nice RGB lights, in one or the other way. And yeah, play sounds, drive your LCD, DMD, right? This kind of stuff. So that's what the control system is for in general. And if you look at this, I mean, sounds simple. We take a PC, we take some GPIOs, we connect the stuff, and it's done, right? That would be the simplest solution, but for some reason we are not doing that. And yeah, let's go a little bit into that. So what are the challenges? So basically we got like something on the left and on the right. So on the left we got rather complex games. So like in the 90s or 80s, 90s, games were simpler. They had one CPU which did all of this. Nowadays, games are a little bit more complex. Rules are deeper. They play sound. They do HD graphics, which require a lot of CPU resources and so on. And not everything can be in memory and so on. So there's like some rather complex stuff going on in the game. So mostly because of graphics and sound, not because of the game logic. Also, light shows became a lot more complex than they've been like in early WPC games. And on the other side, we got latency. And what is latency? Latency means if you press your flipper button, how long does it take until the flipper coil becomes active? So we got this latency. And now if you think about you got a switch somewhere, and then you got your high-level game, which also drives HD graphics and sound, and that should read the switch and act on the switch. You can imagine that this will take a certain time, and even with modern CPUs, it might take a few milliseconds, and that's not great. Furthermore, even worse is like it's jitter. So the humans are really, really good to adjust to latency. So, I mean, if you press the light button in your room, does the light turn on instantly? You might think so, but it's actually not. So, like, especially with bulbs and even more if you got Alexa or something, some home automation, there's a certain time. But as long as this stays constant, you do not really notice this. You press the button and you don't really notice how long this is. And that's actually the same for flipper buttons. This latency doesn't matter so much. So you can have 1 millisecond or 5 milliseconds. You get used to that. After like playing 5 balls, you simply get used to this 5 milliseconds and you take it into account automatically. But jitter is like a lot worse. So if you press the flipper button one time, it takes 10 milliseconds to actuate the coil. Another time it's 1 milliseconds. Then you won't be able to hit shots anymore. So that really, and even short, so even short jitter, like 1 or 2 or 3 milliseconds, that makes, that makes the game feel weird. And especially for that reason, we cannot have a game which runs HD graphic and the same CPU also drives your flippers. So that's a problem. So some manufacturers tried that with medium success, I would call it. But in general, it's not done, and I will show you in a minute how it's done. And then we got something in pinball which are like pretty short switches. So if you shoot a ball through opto, then like this opto is usually active for around like 10 milliseconds max. So you need to be able to read switches pretty quickly. So if for 10 milliseconds, it's 100 hertz, and you should not miss this interval, right? And that's already in, if you also like do HD graphics and load stuff from disk and so on, that's actually like a challenge. So sometimes you might have some lag and you miss switches for 50 milliseconds, and then you actually might miss a shot to a ramp or something. And for that reason, that's also something which is a challenge, right? And also like we need to be accurate. especially when pulsing coils. So in pinball, we run like rather high voltages, and your coils will be active for something like 10 to 30 milliseconds. And like 10 to 30 milliseconds is a huge difference in power. So you want like consistent, for example, you want your shooter to be on a consistent strength, the same for the flippers and so on. So they should also always like activate the coil at the same time. And for that reason, same thing with jitter. It's a problem to do this from a PC. So we need to be really, really accurate, like less than a milliseconds accuracy. So like repetition accuracy. So we pulse it 2 times and it should not differ. That's important. So like those are the main challenges. Just so that you understand what like the background for all of this. Also, obviously, costs is a thing. So you want it to be as cheap as possible and to be as reliable as possible. But those are like more general engineering challenges. So with those challenges in mind, we got like two types of pinball control systems, which we have been seeing lately. In general, all of them, really like all of them, they got like some single board computer running Linux. Maybe like America's Most Haunted with the Pinhack board was like kind of an exception. They actually ran the game on a microcontroller, but any other game that I know, like any Stern game, any American Pinball game, and so on, they all like run some small Linux PCs, right? Like something like this, like a Raspberry, for example. Yeah, also like Stern Spike. They run like like a similar powered Linux PC. They're like how's it called? The Nisi game. TNA, right? Total Nuclear Annihilation runs like an x86 CPU, which is quite powerful, but also like the small form factor and usually like around $100 or a little bit less. And additionally, and now it gets interesting, we got like some embedded controllers, and those are like usually very cheap small controllers, and I would say less than $5, usually less than $1. And so they are really low powered controllers, which run at a few hundred megahertz, single threaded, but they run like a control loop, which is really tight on timing. So everything is like timed in this loop. So first it reads switches, then it disables coils, then it controls lights, and then it begins from the start. And it does this 1,000 times a second, or maybe even more. So that's generally how those work. And then like two kinds. So generally like the Pinhack board or the Pinotauro board, for example, from Ben Heck and Macrofab. They it's like one large board, and there are other large board solutions like kind of like Cobra Pin. And then there are also like those node board style boards. So like Stern Spike, for example, multimorphic P3 Rock, fast system, or like like OPP also. Like I mean the Cobra board is one large board, but it technically has 2 node boards. So it's also like it's kind of also a node board. And those two things exist, right? I would say for larger manufacturers or larger runs, they more go to node boards because it's probably a little bit cheaper because you need less wiring and so on. And for like smaller manufacturers, I guess it's easier to have like one board and then build like this traditional wiring harness because it's less parts. So I guess there's like a trade-off. But it's only like my guess. Yeah, hi Prospector, how are you doing? And yeah, I made diagrams, so prepare. So like this is how the single board controller stuff usually looks, right? So we got your MPF game obviously here, right? So that's like some Linux PC, and that interfaces to the controller usually via USB or some serial. And then we got like one central controller which has all the drivers on it, which reads the switches, and which also controls the lights and maybe also servos and steppers and whatever else you can do. And connected to the controller, you got then switches, called lights, and whatever else. So that's, as you can see, it's really simple. It's probably like the minimal part count, but like this wiring harness here is like really long, and that's rather expensive to make, right? It takes a lot of wire and a lot of work. I don't know if you saw like pictures in the Stern factory how they did that. Like they put a play field with nails and then they pull the wires around it, and so that's kind of manual work. It's not automated. And then we got like node boards. They are similar, but a little bit different. So there again, like your MPF game runs here, interfaces the main controller via USB, and that controller then connects to multiple node boards. Usually there's some kind of bus here, and those node boards then control switches, coils, lights again. So it's kind of separated. And this also like differs a little bit between systems how this actually works. So for example, you probably know the Open Pinball project, and there we interface. So we do not have this controller in the Open Pinball project, but the computer interfaces each of the nodes via USB, and they are more or less independent controllers. Earlier they could chain nodes as well, but not in the latest version, because it's also not needed. And then we simply address those as multiple nodes, right? And this brings certain properties, which we will come to in a minute. And like other systems, like the fast system, for example, there's like one controller here, and then you chain the nodes after each other, and there's like a loop between them. Again, other systems like a P3 Rock, like they run like a multi-master RS485 bus, which is similar to how it's done in automotive. Spike is similar. They also run like RS485 node like bus, and this controller is really like, it's not really a controller in Spike. It's just more like a USB to RS485 converter, kind of a little bit more logic, but that's how this usually works. For the P3 Rock, it's a little bit different. So they run a rather like beefy FPGA here, and their logic runs in the controller. But I think they are the only system which does it. Everybody else has the logic in the nodes. So for example, they actually process the commands here and then only send like sub commands. I don't know how that actually internally works, but they translate it here. So there are like small differences here, but I hope you get the idea how this kind of works. And like there are certain trade-offs for all of this. So I will come to this a little bit in a minute, because all of that has cons and pros. So there's not like a silver bullet or perfect design, I would say. So now I told you that like we got the game here and the controller here, or the control system. So what does the game, or like what does MPF actually send to those controllers? And there are like a few commands which we need. It's not many. It's actually really not many. So most of those controllers got like, I don't know, 60 commands or so. And MPF really only uses like 6, 7, 8, 9, 10. But sometimes one of those commands is actually 5 commands to the controller or something. So like the first and probably quite obvious command is that MPF tells the controller, pulse this coil, so turn it on for 10 milliseconds and then turn it off. Really simple. It's used for ejecting a ball from your trough, firing the auto launcher, stuff like that. Optionally is you can also pulse it with PWM. Often it's a different command then, but we see it like as a parameter to this command. That's done in modern systems to like have longer pulses with a little bit less power. So like Stern Spike does it a lot, and it's available in most pinball controllers. Not in all of them, but in most of them. Then we got like enable the coil, which is keep it active. And in pinball, that's usually done by pulsing the coil first for like 20 milliseconds to actually actuate it, right? And then it should stay active. But if you would put it full power on, then after a few seconds it would start burning and bad things happen. So for that reason you use PWM, and that's basically turning it on, off, with like 3 milliseconds on and 2 off, or like more like 3 on, 5 off, right? So it's like 30% on or something. And again, for the jitter reasons I talked about earlier, that would be a problem to do this PWM from MPF, because we would miss this timing. We wouldn't have like perfect sub 1 millisecond timings for on off. And also it would be a lot of commands. And for that reason, we delegate this to the hardware. And that's actually a command which all except one hardware platform supports. So, and you would say, well, what? There's hardware which doesn't support enable? And actually there is. So Stern Spike doesn't have this command. Instead, for Spike, for example, we just pulse the coil again and again. So that they can pulse the coil for 500 milliseconds. So we just repulse the coil again and again in case we want to enable it. That's, for example, one of the interesting things in pinball controller land. And then, you need to disable. So MPF needs to be able to disable the coil again. This, for example, would be if you have like some lock and you enable the coil to hold the ball. That, for example, could be an enable, and then we disable it to let the ball roll out. And then for lights, we usually get a command to turn a certain light to a certain brightness. Usually 0 to 255, sometimes more, sometimes less. Sometimes that's also only on and off, or only 8 brightness levels or something. That really depends. We always wish for a fade command, so that we can tell the hardware to go to red in 50 milliseconds or something. And that's simply, again, for jitter reasons, because it looks nicer if this is a smooth fade. Because if we fade it in software and send an update every 30 milliseconds, then we might jitter a little bit and it wouldn't look as nice. And with this, it looks really, really a lot nicer. And a lot of hardware supports that, including, for example, Spike, the P3 Rock, Fade Candy, and so on. Then, obviously, quite important, we need to be able to read changed switches. So we need to be able to read switches initially, so the initial state, and after that we need to know changes, right? And ideally, the hardware kind of buffers this. So even if we only ask the hardware every like 50 milliseconds, it would remember that switches change, right? Not all hardware does that. So for some hardware, we have to pull it really, really frequently. Usually at 100 Hertz. And for others, especially like the P3 Rock is really great here. They even give us like timestamps when switches change. So that's really great. And you can then reuse the timestamps to pulse the coil and so on. That's really cool. So they put a lot of thought into that. For other systems, it's often a little bit simpler. But yeah, that's what it is. Then like there's a little bit more exotic stuff, which is kind of like in the back, but it's also important. One is like basically a delayed pulse, so you can tell the hardware pulse this coil in 100 milliseconds. And that's, for example, if you want to time something, you got an opto, and then you got a magnet, and then you want to actuate this magnet at an exact point of time. That's, for example, something which the P3ROC can do. So you can get the hardware timestamps from your switches, calculate some time, and then pulse something in the future and so on. That's really nice. And then there are like two things which come up again and again in our documentation. That's recycle and debounce. And they are like more words for the same thing. So what we understand for recycle is you can tell a certain coil to not actuate again after before a certain time basically passed. So and that prevents kind of machine gunning stuff, right? So for example, slingshots, when they actuate, they should be inactive for, I don't know, 30 milliseconds before they actuate again. To prevent them from staying active, actually, because if you pulse them again and again by error, for example, they shouldn't stay active, because that would burn up the coil. So it's like a protection mechanism, but also it makes, like, for example, slings and pop bumpers a lot like nicer, because they don't machine gun. You probably have seen this in older games, but in newer games you prevent this with software, and you can, not always, but often you can configure how long this recycle time is. Then we got debounce for switches. So like one of the things is that you might, so if you actuate a switch, it might like go on, off, and on. And also like if it goes off, it might go on again after, so like shortly, because it's a mechanical switch, right? And to prevent this kind of double switch hits and so on, you typically got debouncing. And in MPF we call it debounce normal and quick. And we initially called it off, but then in some hardware we actually implemented it in off. So we actually turned it off in hardware, and that got really, really bad. So now it's normal and quick debouncing. And because even if you turn it off in MPF, it's still a little bit of debouncing. Otherwise, it usually floods the bus and hardware will really behave badly. So this is something we can change. And for example, for flipper buttons, it's usually turned down. So you want, for example, be able to have really, really short switch inputs on a flipper button, right? So that you can, for example, post pass a ball or tap a ball and stuff like that. That requires really, really short like switch hits, and for that reason you typically disable or reduce debounce on those switches. But for example, for targets, which are usually really bouncy, they go like this, there we put in more debounce. We put like a little bit of debounce in hardware, and for like if you want to debounce for 100 milliseconds, we do this in software. There's like an ignore window, it's called in MPF. In hardware we debounce for like something like 2 milliseconds for maximum 10 milliseconds, nothing more. And that's also a setting. Then I talked earlier about like this jitter and latency stuff, right? And we want this, that you hit the flipper button and the coil actuates really, really fast. And to implement this, there are like hardware rules. And that's for flippers, pop bumpers, slingshots. Sometimes also, you can also use this for magnets and stuff where timing is critical. For like, even for like a kickback, that would also be an example. And that works this way. So MPF tells like the hardware, when switch X is hit or becomes active or inactive, setting usually, then pulse coil Y, right? So we tell the hardware to do that. And once we send this to the hardware will do it. So then the game is basically out the loop. And it's not like, if you look at this, that like the switch hit goes here to the node, to the controller, to the game, and the game tells the controller to actuate the coil, node tells the driver to actuate the coil, and the coil is actuated, right? Because that would be like a lot of latency and jitter. But instead, the game tells the controller or the node, depends on the hardware, that when the switch here is active, then pulls this coil. And that's then either here or here where this happens. And this obviously like reduces the latency and especially the jitter. So is there a limit on how many hardware rules different systems can handle or remember? As far as I know, not really. So there are like two types of systems. So either they put the rule to the switch or to the coil. So it's actually really really different. So either like you got like a list of rules for this coil. Sometimes it's fixed. So for example, Stern Spike, I think they got like 3. So you can have 3 switches to one coil. I guess like the most flexible thing is like the P3 rock, and there they might have a limit somewhere, but it's probably quite large. And for I think for the Open Pinball project, it's also for the coil. Yeah, it's also for the coil, where you can say this is then mapped to the switch, and there it's also I think a 1-to-1 or 1-to-2 mapping. So I would say you can at least have 1 rule per coil. So maybe more in some systems. For example, fast maps it to the switch. It has some other implications. So yeah, it's I guess there's not really a limit for most systems. So more like the mappings. Yeah. And then like we got a lot of optional parameters here, and that's not even complete. So there's more than this, but just to give you an idea. So optionally, MPF can also tell, or the game can also tell the controller to keep the coil active. And that's what you do for flippers, right? So you hold the button and the coil stays up, and then it's active with PWM. So then it's like it's a 20, 30, 40% duty cycle, and it keeps active until like, yeah, obviously until the switch opens. Then optionally, we can either tell it to cancel the pulse or not cancel the pulse. So like this initial pulse, in some cases, for example, for the slingshots, you always want to have the full pulse, right? It should always push the coil to the end. Otherwise, it would like only push the ball from the switch, and the power would be inconsistent. But for flippers, you want to be able, yeah, to tap the ball, and there like the flipper won't go all the way up, right? And for that reason, it's important that you can tell it to cancel the pulse also. Then like especially for dual wound coils with end of stroke, you should be able to tell the hardware to disable this pulse, or to cancel the pulse when the end of stroke switch opens, right? So that you set like a pulse of 50 milliseconds, and the end of stroke switch then just cancels the pulse if the flipper is open. That's what Stern Spike even does on single wound coils for like, I guess, for power consistency reasons. Then again, PWM on the pulse, that's something which only like half of the hardware supports in MPF. Because yeah, like, so they can do PWM on pulse, but only without like hold. Like a lot of hardware cannot do both of them. But it's sometimes useful. And then like something which I think only Stern Spike currently supports, that's repulsing the flippers when the end of stroke switch opens. So this way that the flippers are up, we PWM them, and the ball hits them really, really hard and pushes them down. Then end of stroke switch opens, and the hardware will repulse this automatically, so that you do not even notice that it actually dropped down. So we emulate this in software in MPF in case the hardware does not support it, but that gives it like a latency penalty of 10 to 20 milliseconds something, depending on the hardware. That's like the most general stuff, and like the first three are like supported by almost all the hardware, and those two by most of the this by most of the hardware, and that's only by Spike. So we do this in software as good as we can, but then you get like some races between hardware and software, right? So when you then release the flipper buttons and we re-enable the flipper, we have to make sure to disable them again, otherwise we might have races and the flippers might stay up. So yeah, but we try our best in MPF to emulate it in software. Optionally, there's also like delay. So that's something, which a few hardware systems can do. I think the Open Pinball project can do it. The idea is that if you, for example, have a kickback and the switch is not directly in front of it, but a little bit up, that you can tell it to pulse the kickback after like 100 milliseconds or something. But then like the timing, the ball has to have a constant speed, so that's not something which is working too well, I heard. And they have even been like some Spike games where they have been like doing kickbacks in software. So where actually the game actually read the switch and pulls the coil. It's not too reliable, but kind of worked. So there are certain constraints, and that's like only certain switch and coil combinations work in most controllers. There are few. So like let's start this way. So for like the single board controllers, most of them at least, any coil works with any switch. Let me think. No, not even there. Even there, they got some constraints, and that not every coil can be used for everything. Yeah. So usually there are some constraints. You can read your hardware manual. And for those node boards, that's often the case that the switch and the coil have to be on the same node board. That's true, for example, for Stern Spike, for the Open Pinball project, for Fast, and so on. For where it's not where it's possible to use like any switch with any coil, is actually the P3 Rock, because they do they run the logic here. So the controller reads all the nodes, the switches of all nodes, evaluates the rules, and then actuates the coils on the nodes. And for that reason, they can actually do they can do any switch with any coil. I think there are I think there are no limitations. And for any other, there are limitations. Like, but the disadvantage is that they have to run like everything over the bus and the P3 Rock. And like other systems like Spike, for example, do it node local. And in this machine where they had the kickback in software, they apparently like messed up the hardware wiring. So the switch from the kickback was on one node and the coil has been on the other node. For that reason, they had to do it like here in the game. For example, Fast Pinball, they got something special because like they chain the nodes, and there you can use the first 8 switches of the first node on rules of on all nodes, because like I guess they forwarded on the bus then here. And for all other switches and coils, it's only like node local. And for the Open Pinball project, for example, it's also only node local. Spike is the same, and so on. But that's something which you have to look up in your pinball controllers manual. Right. And like not every controller supports everything. So MPF tries to fall back to other things so that it kind of works as good as it's possible. And if we can, we emulate it somehow in software, or like we use other commands to emulate it somehow. But yeah, that's the reality. It's a little bit different for all of them, and also with the commands, they are quite different between systems. So now you probably figured this out by now, I guess, maybe. So now this question again. So why do my flippers not work with keyboard bindings in MPF? So I bound like S flipper left to my keyboard and doesn't work. Yeah, and the answer is obviously that MPF tells the controller that this should happen, right? And the keyboard mapping, so there's no way for MPF to tell the controller that the switch changed. That's only something which the game knows. And for that reason, this hardware rule will not trigger in this case, right? So it's pretty simple, but that's the answer why that doesn't work. So maybe we will emulate this as well, but currently it doesn't work. And then the next question is something which we kind of benchmarked along the streams for the hardware which we looked at. So it usually in most hardware systems which we benchmark takes around 1 millisecond between acting the switch and the coil becomes active. So it's actually really, really fast. 1 millisecond is, yeah, it's nothing for human. And yeah, but I'm actually pretty certain that you wouldn't even notice for like up to 10 milliseconds. So like a delay for up to 10 milliseconds wouldn't be noticeable for, yeah, like for player, right? So even for professional players, I don't think they would actually notice that too much. What they notice is actually the jitter. So how much this jitter is. And we also measured this, and that's far below 1 milliseconds for all the systems we looked at. Usually like so small that we couldn't really measure it, but our like measurements weren't too accurate. So probably less than 1/10 of a milliseconds. So yeah, that's the answer to that. And yeah, I hope you found this overview about hardware interesting. And that's also what I prepared. So only slides today. I was told never to tell thank you or any questions, so I put keep on hacking here. But if you got any questions and or if you want to know specifics of like some system, we can talk about it. We can also look into MPF source code if you want. It was a lot of fun. Hope you learned something, and yeah, have a great night, and yeah, for the people on the other side of the ocean, have a great day, and until then, see you soon. Keep on hacking pinball.